Calculations involving acidic and basic solutions. We'll look at using Ka to do various calculations with weak acid solutions, as well as finding the pH. Do the same thing with weak base solutions, and look at how to do calculations involving finding the pH of polyprotic acid solutions. So we're going to start off by looking at weak acids. We're going to look at their percent ionization, their Ka, as well as their pH. So first off, percent ionization, when you put an acid into water, a certain amount of it's going to dissociate. You can express that as a percentage. And so we start off with our acid molecule with the hydrogen ion attached. It's going to shift to the right to some extent before it establishes equilibrium, and that'll give you some amount of hydrogen ions. And do remember that when we say hydrogen ions, we really mean that the acid is acting with water, and this hydrogen ion here is really a hydronium ion, but we're just being lazy and calling it a hydrogen ion. But it really is attached to a water molecule, so you'd have to have water on the left if you wanted to get that to balance. So most weak acids are going to ionize less than 50%. And so we can express the percent ionization just as any other percent calculation, where we are saying which portion of them are actually ionizing over how much could have ionized, or the total amount of acid. We could also rearrange and solve for, okay, based on the percent ionization, can I find the concentration of the acid, which we could then use to find pH. So same equation, just solving for a different variable within it. So if we know the pH, we can turn that into, using our pH calculation, into our hydrogen ion concentration, and then we could use that to find the percent ionization by using this above equation here. So let's try it out. So if we have a percent ionization, or sorry, we're trying to find the percent ionization, we have the concentration of a solution of this particular methanoic acid, and its current pH is 2.38. So remember, its pH tells us how many hydrogen ions it has put into solution. We know that the acid molecule itself, its concentration was 0.1 moles per liter. A certain amount of that is going to go through with the dissociation, but not all of it. The amount that did would have contributed to the pH, or the concentration of the hydrogen ions. So we can find out, okay, well, how many hydrogen ions would it take to get that pH? What portion is that of the actual concentration? And then we can express that as a percentage. So first, find the number of hydrogen ions by using the pH. So 10 to the power of negative pH is going to give you the hydrogen ion concentration. And that tells us that 4.71 times 10 to the negative 3 moles per liter is how much actually did dissociate. So again, if we have this acid here, so we can generically just say, there's the acid. We could actually put the real formula in if you want as well. And we know it's going to be dissociated into the hydrogen ion and whatever's left over. So the real equation would involve your methanoic acid acting with water, and I would donate that hydrogen, forming the ion here. Oh, that's supposed to be a 2H, and that would have a negative charge, and the water would be what's actually hanging on to the hydronium ion. But we can just use our generic equation for a weak acid and say, okay, what's really happening is it's going to give a hydrogen, that's for sure, and there's going to be something left over. So the generic equation is a fine way of thinking of it as well. So the amount that actually did dissociate was 4.17 times 10 to the negative 3. Now we started with 0.1 moles per liter of this acid, and only 4.17 times 10 to the negative 3 actually dissociated. So if we express that as a percentage, we have our percent ionization. So take the portion that did dissociate, which is the amount of hydrogen ions that were created, divide it by the total amount that we had, the 0.10 moles per liter, multiply by 100, and we should end up with a 4.2%, using two significant digits, as we have our concentration in two significant digits, and the decimals on the pH, because it's a logarithmic scale, there's two decimals, so that's also two significant digits. Ionization constant, so this Ka value tells us the proportion of the reaction that goes to form product. Because remember, the equilibrium constant, the K, is products over reactants, so whatever the Ka value is, it essentially tells us how much is actually shifted to the right versus how many reactants are left there. And since this is a weak acid, a certain amount of it is going to shift to the right, but not all of it. So the Ka formula for these can be written as just as any other equilibrium expression. K is equal to the concentration of the products over the concentration of the reactants, and these are all 1-to-1 molar ratios, so all of these have exponents of 1, So these are real simple equilibrium expressions to write. But again, whatever the Ka is, and we're using that A to mean for the particular acid, whatever the Ka is tells us how much the reaction has shifted to the right, how much the acid has actually dissociated. And since they're weak acids, we should be dealing with relatively small Ka values, or in this case, Ka values. So the Ka of an acid can be calculated using the percent ionization, using the equilibrium concentrations, and the ionization expression, which is what's happening at equilibrium. Let's have a look at how that works. So calculate the Ka. So we're actually looking for the Ka of this acetic acid. If you have a 0.1000 mole per liter solution, it has a percent ionization of 1.3%. So essentially we're given the total amount of acid we're dealing with. We're indirectly given how much is actually dissociating. It's going to be 1.3% of the total. And then we're going to solve for the actual Ka value. So let's have a reaction to look at. And again, if you wrote the generic reaction and said, okay, I've got a weak acid, it's going to establish equilibrium with a hydrogen ion and leave behind this anion. That way, that's fine too. Again, it doesn't really matter what it is. The generic expression is going to work just fine. So for this, just because we have sort of an initial concentration and we have a change and then we're going to have these new equilibrium concentrations, it does help to use an ice table to keep track of these variables when you're first starting out. So I'm going to build an ice table below this reaction here, and I'm going to look at the three species within the reaction, and I track them initially, what they changed by, and what they will be at equilibrium, so that I can use my equilibrium row here to solve for my Ka value. So there's the number that we have. So initially we're starting off with the 0.100 moles per liter, and at that point we would have no products being formed, none of it has dissociated. A certain amount is going to dissociate and give us our new equilibrium values, which also are and our cation here, the hydrogen ion is going to increase, and our anion is also going to increase by some amount. If we take those three amounts and we plug them into our equilibrium expression of the hydrogen ions and the anions, their concentrations over the original, reactants equilibrium concentrations, then we'll be able to find out the K value, or in this case, because we're dealing with acid, we call it Ka. So let's work through that. So the change in, first, we know it's changing by 1.3% because that's the amount that actually ionizes. So the question is, what is 1.3% of 0.1? Not very much, 0.0013, and again, I'm just writing 1.3% as a fraction, so 0.01, just divide that by 100, and we're writing it as a decimal, and so if you multiply that by the initial amount, it'll tell us how much it is actually changing by. So that gives us our decrease in the concentration of our acid. It was 0.1, it's going to drop by 1.3%, or 0.0013, which also gives us, and again, as soon as you have any number in a nice table in the change row, you then have all of the numbers as long as you follow the molar ratios. And since this is a weak acid equilibrium, it's all 1 to 1 to 1. So hydrogen ions are going to go up by 0.0013, and the anion, whatever it is, in this case the acetate, is going to go up by 0.0013 as well. So that gives us our equilibrium concentrations. We then put those into our equilibrium expression, and I would recommend actually writing out the generic equilibrium expression with the hydrogen ion and the acetate ion and the original acid. So when you have more difficult questions with more things to keep track of, you don't end up mixing them up. And you know that, okay, we've got a hydrogen ion here, we're still dealing with Ka here. Plug in the numbers and you have your Ka. So pH from this. Ka can be used to find the hydrogen ion concentration. And once you have hydrogen ion concentration, it's just a quick jump over to pH. So calculate the pH of a 0.1 mole solution, mole per liter solution. This is acetic acid again, and they're giving us the Ka of 1.8 times 10 to the negative 5. We want to find what the pH is. Now, realize that the pH is going to be the concentration of the hydrogen ions. This is based on that. And obviously this is an acid, so it's going to be contributing to hydrogen ions, but water does autoionize, and it does contribute as well to the pH ions. The hydrogen ions, which would then be translated into pH. But really, this is negligible. So that small amount that is being provided by the water can essentially be ignored, and we can just look at the acid itself as the sole source of hydrogen ions to find the hydrogen ion concentration. So again, we've got our equation. I'm writing out the acetate ion slightly differently this time. It's cool, just an easy way to remember it. So this acetic acid is going to dissociate and form hydrogen ions and acetate ions. We know that we have a 0.1 mole per liter solution of this acetic acid, and we know what its Ka value is here. So we need to find out, okay, well, what amount of hydrogen ions are we going to get? That's what we're looking for. Then we can turn it into pH. So to do this, we're going to find the hydrogen ions at equilibrium. And so, again, we want to know an equilibrium concentration. We have an initial concentration. It helps to build these or keep track of these numbers using an ice table. So same thing, set up your reaction. I've rewritten it as an acetate ion here. We know our initial concentration for our acetate ion. We know that we have 0 moles per liter for both of the products. They're going to change by some amount, and we don't know what the percent ionization is in this particular case. So we know that it's changing, but we don't know by what. And so we're going to use the variable x. And if the acetic acid is going to go down by x, then we know that these two are going to be going up by x. So we end up with 0.1 minus x and x as our equilibrium concentrations. So we can put those into our equilibrium expression with our Ka value, and we can solve for what x is. Now what I can do, and I'm going to do here, is I'm going to use this 100 rule to see that I can ignore x. And again, if my concentration is divided by the K value, I can get an idea of what sort of change we're going to be seeing. How much is this going to be shifting to the right? How much product is going to be formed here? And then what I'm trying to find out is, okay, if I ignore the X value when relative to this particular concentration that I'm starting with, would that be okay? Is it going to be significantly different? And so I'm checking the concentration divided by the K value and seeing if that works out to be over 100. It does, and so therefore I can ignore X. So when I go to plug them into my Ka expression, I'm going to plug in the two X values for the product, and I'm just going to put in 0.1, and it is going down by X. But using this 100 rule here, I'm saying, okay, this X here relative to this 0.1 is essentially insignificant. So it'll change 0.1 by a little bit, but not very much at all. So I can just not subtract it, and I'll pretty much end up with 0.1 anyways. And so I end up with an X value of about 1.3 times 10 to the negative 3, as well as a negative 1.3 times 10 to the negative 3. I know that I can't use the negative value because I can't have a negative concentration, and in this case X represents a concentration, so it has to be positive. I can then take this because this represents the concentration of my hydrogen ions that I saw in my ice table. So if I take the negative log of that, I've got the pH. All right, weak bases, we're going to look at the Kb for weak bases, so the equilibrium constant for weak bases, as well as the pH, and of course with bases we may want to write that as pOH. So the ionization constant is the Kb value for bases, and essentially this is to what extent the weak base is going to be picking up hydrogen ions. And when you're dealing with a base, we can think of them as taking a hydrogen ion from water, and so they are now going to have that hydrogen ion, and they're going to leave behind a hydroxide. So this, as long as it's a weak base, this is going to have established an equilibrium with a certain amount on each side. The extent to which it shifts to the right can be expressed by this Kb value for that particular base. So then the equilibrium expression for a base is going to be the hydroxide that gets produced, as well as whatever cation is produced, whatever is formed once it picks up that hydrogen ion. Not necessarily a cation, but it's definitely going to be picking up a hydrogen ion, and that'll be divided by the concentration of the original base. So the Ka of an acid can be related to the Kb of its conjugate partner. So if we had an acid, so let's take our generic acid, a hydrogen attached to an anion, and if it goes through reaction, actually let's put water in this time. So let's say it goes through with water. In this case, water is going to be acting as the base, and you'll be left behind with this anion, and you're forming a hydroxide ion. So this acid and this anion, they are conjugate partners. They differ only by a hydrogen ion. So the to the extent to which this shifts to the right, we could think of that as being the Ka of that particular acid. Now, its conjugate partner here is a base, it's a conjugate base. So if it were to work backwards and pick up a hydrogen ion to come back and reform that acid, it's acting like a base. So it will have a particular Kb value. And these two values, so the Ka and the Kb, they are related to each other through this equation. The Ka multiplied by the Kb are going to give you Kw. So using that, we can figure out, okay, well, what is the Kb for any base that we're talking about here? So let's deal with this nitrite ion, so NO2 negative. So that's a particular ion, and it can act like a base by picking up hydrogen ions. So if it did pick up a hydrogen ion, it would form an acid. If we look at the acid that it would form, so let's say, okay, here's your nitrite ion, and let's say it takes a hydrogen ion from water, it would form this acid. So these guys here are conjugate partners. Moving in this direction, it's acting as a base, so it will have a particular Kb. This acid that it's formed, its conjugate partner, if it were to go backwards, it will have a particular Ka value. So what the question's asking for is, what is the Kb? And we know, as soon as we find the Ka, we can say, okay, well, I know that Kw equals Ka times Kb, only for conjugate partners. But then if I know the Ka of this acid, I can find the Kb of its conjugate partner base. So you're going to have to use a table and look up the constant, the Ka value, and often you'll have a Ka table with you that you can use, or you can just research what is nitrite's Ka value, look it up on a table, and then we can do the calculation. There could be Kas and Kbs, often though that you're going to find the Ka much more easily than you find a Kb, but we've got a very quick equation that'll run you through to the Kb. So the Ka of this nitrous acid, HNO2, if it is 7.2 times 10 to the negative 4, we can plug that into our expression here. So we know that Kw is 1 times 10 to the negative 14. We know that Ka in this particular case is 7.2 times 10 to the negative 4. So we can solve for Kb, and we can say that the Kb of this particular acid, this nitrite ion, its ability to be an acid, it can be expressed by the Kb of 1.4 times 10 to the negative 11. pH of these bases, again, we can translate this into a concentration. We can use the Kb, and we can find out, okay, what would the concentration of hydroxide ions be? And from there, we can find the pOH, and then actually from the pOH probably quickest to find the pH. But again, once you have the hydroxide ion concentration, you could also find the hydrogen ion concentration, and then from there you could find the pH. So lots of different ways of doing this. So let's say we had some tonic water, and it is a weak base, that's why it doesn't taste good. And so it has a concentration of 1.7 times 10 to the negative 3 moles per liter. Find the pH of this tonic water, given that it has this particular concentration of a weak base, and we have the weak base's Kb at 3.3 times 10 to the negative 6. So essentially, if we can find out how many hydrogen ions there are in that tonic water, we can then go eventually to what the pH is of the water. And you'd assume since it's a base, it should be above 7. So here we are with this equation. And again, this is the lazy version of the equation. If you wanted to write out what's happening with the water, so that the base is going to be picking up a hydrogen ion from the water, because as written right here, it doesn't balance. So if you are bothered by that, throw the water in, and you can say, oh, that's where that hydrogen ion is coming from, and that's where that hydroxide ion is coming from. But if we're dealing with this equation in an ice table, we know that water's concentration is not going to change. So if you really wanted to have that water in and have a column for it, we just wouldn't put anything in for that column because its concentration does not change. So there's no point in keeping track of it through the sequence of events. We do know the concentration of the base is 1.7 times 10 to the negative 3. Initially, before any dissociation happened, you would have no of the cation being produced and no hydroxide ions being produced as well. We know it's going to be changing by something, so some amount of it's going to shift to the right. That's what our Kb will help us figure out. So it's going to be going down by x, and so I can use the up by x for the amount of products formed, and I have my 3 equilibrium values, which I then can plug into my equilibrium expression and solve for x. And again, if you want to ignore this x here, you could check the 100 rule and say, okay, is this x going to be small enough relative to the concentration here that I could probably ignore it? So whatever value it is, if I took it away from 1.7 times 10 to the negative 3, it wouldn't change that number significantly. So would I be able to ignore it? So you divide, again, you check the number that you're using it against, the concentration, divided by the K value. In this type, it's the KB for this base. And we're saying, okay, well, how much is it actually going to shift to the right? And that ends up with a number that is over 100. So we're essentially saying there's not going to be enough of a shift to the right to really influence this initial concentration. So let's just pretend the initial concentration doesn't change. So we're putting in the KB value for the base, the concentration of the cation that's produced, as well as the OH, because remember, one of these X represents the concentration of the OH ion. And there's our 1.7 times 10 to the negative 3. And remember, this really is minus X, but checking the 100 rule says, okay, this X here is going to be pretty small, that it may as well just be ignored. The denominator on that side is pretty much going to be 1.3 times 10 to the negative 3 anyways. So you solve for X, and again, no negative concentrations make sense, so we have to ignore that one. Don't forget, and this is probably one of the reasons why you want to write out the main generic equation, is so that you remember X is a hydroxide ion concentration. So once you have what X is, if you take the negative log of it, you end up with the POH, because it's a hydroxide. So just don't confuse it with being a hydrogen, and you can make sure that won't happen if you actually write out the equation. You'll remind yourself, oh yeah, that's OH. So when I take the negative log of it, I get the POH, which is 4.13, not the pH, the POH. If I then want to know the pH, I know that my pH plus my POH equals 14, and therefore, that's a plus sign, therefore, if my POH is 4.13, then my pH must be 9.88. All right, quick note on polyprotic acids, and essentially, well, you're going to think about them for a little bit and then realize that they're not as hard as they seem to be. So polyprotic acids will lose more than one proton, but we're going to treat this as if it happens sequentially, one proton at a time. And so therefore, if it's going to be losing one proton, there'll be a Ka for the loss of that one proton. And so it'll be the first Ka, so the first ionization. It is also much larger than any subsequent ionizations. So if we had, let's say, I don't know, carbonic acid. So carbonic acid, and it's a weak acid, so it can lose a hydrogen ion, but don't be just a huge amount, and it will leave behind a carbonate ion. So that happens, and this will have a certain Ka associated with it. Now, bicarbonate that gets formed here is also an acid, so it could also establish another equilibrium where it lets go of a hydrogen and leaves behind a carbonate ion. And so this also has a Ka associated with it because it's an acid losing it. So let's call that Ka2, and this is Ka1. So this Ka1, the first time a polyprotic acid loses a hydrogen, is always going to be much bigger, that's a big arrow, than the subsequent ionization. So both will happen, one and then the other, but the first ionization is much, much greater than the second ionization. So what we can do is, so this Ka1, the first one, is going to be quite a bit larger, normally many times. You can take a look at the Ka values for polyprotic acids, but generally it seems to be several factors larger. And so essentially what we need to do is, if you wanted to find the pH of an acid that was a polyprotic acid, all you need to worry about is the Ka1. So just find out, okay, based on that first Ka, how many hydrogens are going to be released? And then from there, you can find the pH. There will be more hydrogens released in the subsequent ionizations, the Ka2 and maybe the Ka3 if it's phosphoric acid, but they're so small that that first ionization is really all you need to worry about. So essentially the calculations end up being relatively easy as long as you're not doing super analytical numbers. You can really just worry about that first proton dissociation, which creates the most amount of hydrogen ions, and then use that to find your pH. Bases can do the same thing, where you have them picking up more than one proton. They pick up one, and then they go through another one and pick up another one. Same thing. The first one is always greater, and so again, you can generally base the pH on the first gaining of the proton, just as you can with the polyprotic acids in terms of the initial ionization to determine the pH.